Okay, so I am recording right now. Hi, everyone. We move on to chapter 2. At the beginning, it's the first example we see is information theoretic security and one-time pad as its realization. And we see limitations of that, and that will essentially position everything else that we are doing, which is that we will, in all the cryptographic, almost all the cryptographic constructions we'll see in this class, we'll need so-called computational assumptions, that hardness of some problems, and we'll need to state what exactly that means that the computational problem is hard, and what does it mean that some security notion is achieved under such assumptions. And at the beginning, we don't have them. Here is the one sort of nice, happy place where we don't need them, and unfortunately, you will see limitations of that quite soon. Okay, so here we go. You know, maybe can I ask one student, maybe like Bruno, to monitor the chat? So if somebody says something that I should, you know, and for some reason doesn't speak up, maybe raise it to the, you know, and so that I stop lecture, because it's a little hard sometimes to monitor a chat window and lecture at the same time. Bruno, did you hear that?
Sorry, I didn't hear what you just said.
Okay, I just delegated you that you monitor the chat, so that
okay, yeah, sure.
says something on the chat and you bring it up, because it's hard to monitor. Okay, thanks. All right, so here is the we'll first define a one-time cipher. So a cipher that a key can be used once. Again, this is just the beginning, right? So we have to start somewhere. For that, we need three spaces. Space where the key is going to be chosen, key space. A space where we say, okay, this is the space of plain text that our one-time encryption will process correctly. So you can encrypt as long as the message is in this space. So this is a typical thing that, you know, you can encrypt a message that has only 160 bits, and if you want more bits, then, well, you know, tough luck. You have to do something else. And here, ciphertext space. Well, actually, ciphertext space is kind of implied by the key space, message space, and the encryption procedure. In addition to these, you have two efficient, which means polynomial time, algorithms, encrypt and decrypt. And for now, you can think of them as functions, which basically means that you think of them at first as deterministic algorithms, right? So a deterministic algorithm is like a function given an input that is a pair of first element in the key space, the second in plain text space. This algorithm follows some deterministic procedure and outputs an element in this space, right? So basically, it's a function for any k, comma m, it assigns to it some ciphertext c. Decryption is a kind of an obverse function. It takes a key and a ciphertext and outputs some element in the plain text space. And for this to make sense, this is like a completeness or correctness requirement that for any message and any key, if they are in the proper spaces, so key was chosen correctly, message was from where it's supposed to be, then if I run a decryption function or a deterministic decryption procedure on input, a key, this one, and a ciphertext, which is an output of the E function or the deterministic procedure on input K and M, then D should basically work as an inverse of E. So whatever E did with the key and a message, applying D with the same key is going to basically bring the message back. So I need this for obvious reasons that what the encryption should give, right? Is that if somebody communicates, a sender has a key, and he runs the E function on his key and a message, sends the ciphertext over, the receiver uses the D function and the same key. If they plug the ciphertext, they should get the same message back. That's what this equation says. So it is the correctness property that decryption reverses encryption on all keys. You can have some relaxations of this, like you can be, okay, perhaps there is a negligible fraction of keys on which this would fail. That might be suffice in practice. We won't worry about this for a while. In practice, encryption is often randomized. So this procedure, in addition to a key and a message, takes sort of a third input, which is local randomness, some coin tosses, so that the encryption algorithm, the randomized one, will come up with the ciphertext. It's, for the same key M, it will not always be the same ciphertext, and yet this should always work. So what will be added for all random choices of encryption? But you can also think like, okay, so this is explicitly encryption is randomized, so perhaps it would make sense to think of this as the probability that this equation holds is almost 1, which is close enough to 1, where the probability goes of the randomness of encryption. Decryption is almost always deterministic in crypto systems we know. So it's rare that randomization in decryption is helpful. Although, surprisingly, there are such cases too, where it might help in arguing security that decryption is randomized. Later on, we're going to add to the pair of these algorithms, encrypt and decrypt, a third algorithm, generate the key. For now, we just think of the key as uniformly sampled from this key space. But some encryption algorithms will create keys in a more complex way. You can actually always think of them without loss of generality as a key space, because define the key space as all the outputs of key generation for all the randomness it can have, right? But sometimes it's good to have the key generation explicitly. Okay, here's a tool.
So, Professor, you got a question in the chat.
Yeah.
Do you want me to read
it? Of the random D algorithm? So that's what I say, like, no, D is deterministic.
You say that sometimes D can be randomized also.
So I'm saying, like, if you stick around in the class, maybe you will see later on why sometimes, in very rare cases, randomization and decryption might be helpful. But that's like way beyond us right now.
An encryption algorithm is randomized. So if there are two occurrences of one value, let's say value is A, so A will be mapped to X and another A will be mapped to Y. But if
wait, it's the same or?
No, there are two keywords. Let's say one is A and another keyword is A again.
It's 2 or 1?
No, there are two keywords, two different keywords.
Wait, no, there's no keywords. There's key and there's plain text.
Yeah, plain text. So there are two plain text.
Okay.
Okay, and both plain text are same. They are identical.
Okay, so it's 1.
No, but I am giving this thing
okay.
2 times.
Let's take it offline. Then, all right. So, okay, so it's the one plain text. Okay, it's called A, and then.
Yeah, and then I execute encryption function. It will give me some ciphertext C1.
Yeah.
And then again on the same plain text, I run encryption function, and then it will give me ciphertext C2.
Exactly.
Yeah, and whenever if I execute a deterministic function on C1 and C2, they will give me plain text A.
Yes.
But what will happen if a deterministic algorithm is randomized? What they will give me?
Look, yes, it's a little counterintuitive that encryption is randomized and it creates different ciphertext for the same message, right? So it like samples ciphertext from some space. And yet decryption has to invert it for all possible outputs of E. Yes, we will have to do that. You will see it's not such a big deal. Like very often you will see why it's useful to have randomization. And of course, you will have to do the decryption, which which somehow collapses all these randomized ciphertext back to the same plain text. Well, that's what we have to do. There will be soon enough a reason why encryption needs to be randomized, but we're like looking ahead, right? So first, like let's think of, like I'm saying, think of them as deterministic now.
Yeah.
They will get randomized in a few weeks.
Yeah. Okay. Got it. Thank you. Yeah.
Okay.
Thank you.
Very good. Okay. So this is the information theoretic secure encryption we'll see. It's basically something called one-time pad, which is nothing else but XOR. It's just a simple XOR between a message and a key. So let's look at some properties of XORs, and first of all, define XOR on long bit strings. So here is the truth table for XOR, right? If X, Y is bits, XOR is a addition mod 2, right? 0, 1, 1, and here it will be 2, but because I do mod 2, so I get back to 0. Okay. Now, that's normal definition of XOR as a gate, right? As a Boolean gate. It works on inputs which are just bits. But I can extend it to bit strings. So I take 2 bit strings here of length 6. That my X is a 6-bit string, and my Y is also a 6-bit string. And how do I do XOR between 2 bit strings? I do XOR pairwise, so position-wise. I apply this XOR function at every index, right? So it works independently on bit position. So I can think of XOR on bit strings of length n as n little XORs, each of them acting on their position, right? So here is 0, 1 XORs to 1, 1, 0 XORs to 1, 1, 1 XORs to 0, this XORs to 1, this to 1, this to 0, and this to 1, right? Okay. Here is the property we'll use. In these extra slides, I said, read up some probability review, and RV is a random variable. Okay, so this is the space of the random variable. So how do you read this? What is this? This is a set of two values, 0 and 1, right? So this set is a set of bits. And what does it mean, a set to the nth? It's a set of strings over this alphabet. So 0, 1 to the n is a set of all bit strings of length n. Okay. So review this and make sure that you remember like what a Cartesian product is on sets, right? These are bits, cross bits, cross bits, cross bits, and times n bit strings. So y is a n bit string, and it's a random variable. So think of n as 100. Okay, I'm going to say 100 bits. Okay. So think of like some, okay, maybe, yeah, okay, yeah, like, so I'm going to pretend like that the IP packet is 100 bits. It's not, it's much longer, but okay, that you have some message that was 100 bits. Now it came from some distribution. Maybe this message Y encodes, maybe you know that this in this application, it's an email. Okay, so it's basically encoding of a fragment of an email. And let's say you know that this person is writing in English. So this gives you certain distribution on these 100 bit strings. Some bit strings don't encode in ASCII an English letter at all, let alone an English word. let alone a sequence of words that make some sense in the language, right? So all of these are constraints on a possible 100-bit strings. And they, when somebody writes something, it's like they have some distribution in mind. They can say one way or another way. First of all, they can say, I will give the student a D, or I will give the student an A. And perhaps, despite the student wants to know which one was said, right? So importantly, the message is not a random string, but it is some string, and it comes from some distribution. Okay, think of another string, X, which is purely random. So a uniform distribution is, these are again n-bit strings. And when I say that X is a random variable over n-bit strings, which is uniform, that means that it's randomly sampled from that set, right? So X is just a uniformly sampled element from the space. In other words, X is a random n-bit string. Okay, so X is a random n-bit string. Y is a random too, but not uniformly. It's not completely random bits. It's perhaps bits that encode English sentences of length 100 bits. Now I XOR the two strings. I XOR the purely random one and the one that came from some distribution. I don't know what that distribution was, some complicated distribution. And no matter what distribution this came from, because X is purely random, if I XOR the X string with the Y, what I get is a purely random string. So that's the beauty of XOR. In a sense, by XORing Y with X, where X was purely random, uniform, I obliterated any information that was in Y, because Z is a randomly sampled uniform bit string. And look, that this is true independent of what Y is. So for example, you can think of a limited distribution where Y is always equal to a sentence, you are like the best student in this class, like I want to make you, I don't know what. If you XOR this message with a purely random string, you're getting a uniform string. Now, let's think of another example, that Y is yet a completely different string. Like, I'm going to, this student annoys me horribly. Like, I mean, he just cheats and terrible person. Let's kick him out of the university, right? A completely different string. But here I XOR it with a uniform n-bit string. So Z is a n-bit, again, a uniform one. I will use it in a few slides, precisely in that way.
Professor, you're assuming they are independent, right? Because yes. Y could be X.
Yes. They are independent because this guy is a uniform random variable. So it's independent on anything. This guy, just because it says uniform. Yeah.
But couldn't they both be uniform but be the same?
No, yes. So, okay, good. So sure, if you look only at one, and then yes. So this is an independent uniform random variable. Yes, correct.
Thank you.
This is assumed to be independent. Thanks. Good point. Okay. So let's prove that this is the case, and we'll just do it position-wise, right? Because if you remember how XOR worked, it was an independent. It basically, I can think of an XOR of a string as n instances of a little XOR, each one working on just a corresponding bit position. Okay, so let's do this for just a 1-bit string, and the generalization to n-bit strings is a simple one. Independently, it works the same for every position. Okay, so in particular, it would imply that if I prove it for just 1 bit, so if I use it on the first bit, the first bit of the X is random. And by this proof, the first bit of Z is random, independent of Y. If I use the same lemma on the second bit, I'll be because, well, the second bit of X is random, so therefore the second bit of Z is random. And so you can see how it generalizes to showing that it works for bit strings of any length. Okay, so let's do it for a single bit. So Z is a bit, right? Because now both X and Y are just bits. Again, X, a fresh uniform random bit, Y, arbitrary. Okay, so now when is this bit 0? In two cases, where both X and Y are 0, and also when X and Y are 1, right? Because that's how XOR works. This is 0 exactly in these two cases when we're talking about bits. So this is an OR, but either case this happens or this happens. It's exclusive. So I can rewrite this probability as the probability that this happens plus probability that this happens, right? Because they are not intersecting. So let's look at the distribution. So X is a purely random bit. So it gets 0 and 1 with a probability 1/2 each. Y is arbitrary. So perhaps it's 0 with some probability and 1 with some other probability. The key thing, the only constraint is that they sum to 1. So P0 plus P1 must be 1. But otherwise, they can be anything. So now I can compute this because, okay, so let's look at the distribution X and Y together. There's 4 choices, 0, 0, 0, 1, 1, 0, 1, 1. And now by the assumption that X is independent than Y, right? That was the key thing that the student pointed out. I compute the probability this happens as a product, because that's how independence works. The product of the probability that this is true and the probability that this is true. So it's P0 times 1/2. Here, it's basically bit X is this attains this value with probability 1/2. So all I have to do is look at the probabilities of these and divide them by 2, right? Because I would just be multiplying P0 by 1/2 and P1 by 1/2. Here P1, here P0, here P1. And so I now check that I'm interested in these two rows. There are P0 half plus P1 half. And they sum to 1/2 regardless of what P0, P1 were, right? Because P0 and P1 must sum to 1. Right, so P1 is simply 1 minus P0. This is kind of, intuitive, right? So basically, it's like if I told you that we can play 2 games based on some secret message I hold in my hand, which is either 0 or 1. I will flip a coin and keep it the way it is if my bid is 0. Or if my bid is 1, then I'll flip a coin and flip it once more. Is the distribution of coin tosses depend on my bid? If the bid was 0, then the distribution is half-half because I throw a coin and I don't flip it. If the bid was 1, the distribution is still half-half because I throw a coin and I always flip it. That's the same. It's the XOR here. The X is the coin. The Y is a pointer that says either leave it, in this case, if X is 0, keep the coin, Z is equal to Y. Or if X is 1, then take the coin and flip it. 1 becomes 0 and 0 becomes 1, right? And the distribution of these coins that come out is exactly uniform, again, independent of this bit that I had, my secret bit that determined whether I leave the coin the way it is or whether I throw it and flip it. Okay, so good. And here is the one-time pad, right? So that XOR encryption is the one-time pad encryption. It was given by Vernam during the First World War. And in fact, you have seen an example of a one-time encryption or a one-time pad in a sense. So a shift cipher, if you think of this, if you squint your eyes, it is a one-time pad also, but over a different alphabet. We have a message space is n-bit strings, and a key is also n-bit strings. And so in other words, in order to encrypt an n-bit string, I need a key that is a random n-bit string. Okay, and the ciphertext that result will also be n-bit strings. And the way I encrypt is I XOR. Okay, hold on. Sorry about that. I don't know if you guys heard this, but somebody is trying to call. Just, I'm sorry, I have to like break just for 20 seconds or so. Sorry about that. It's not gonna work great for anybody who tries to look at it on a YouTube afterwards. Okay, apologies. Okay, so here's the XOR encryption. You take a key and a message and you XOR them. There are two n-bit strings. And to decrypt, you do the same operation, really. This operation happens to invert that one. So, okay, so here is the same example we had. Now, now you take a key and you XOR. Let's see what XORing the ciphertext with the same key gives, right? And it is, so you can check correctness by checking this. So decryption under a certain key of an output of encryption under a given key of a message. What does this return? Well, E of K of M is a function. It's defined to be K XOR M. So I plug it in. D of K and whatever is a function. It is K XOR that whatever, right? So I do that. I replace this with K XOR whatever is in here. And then you can recall that the way XOR works is that it is associative. So when you XOR strings, it doesn't matter what order you do. Like as long as you XOR them out in any direction, in any order, they do create the same thing. Okay, so we can do this flip, right, because of the associativity. And another thing about XOR is that if you XOR a string with itself, it's a 0, right? So if you look at the XOR table, you will see like XORing a bit with itself, it always gives you a 0. So this is a 0. And a third thing is that if you XOR a message with all zeros, that works as an identity. That doesn't do anything, right? Because like XORing a bit string is based on the bits. You either flip or you don't. If all your bits are zeros, they all are like don't flip, don't flip, don't flip. It's an identity. So this shows that decryption reverses encryption. And you can do an example, right? Like where you take the same XOR, the key, you copy it here, and you perform the XOR back, and it's going to invert, right? Okay. Okay. So one-time pad is, it's a great encryption because it's very, very fast, right? Like all you do is XORs. So far, so good. And in fact, during the First World War, right? Like when you did it with a pen and pencil, or even some electrical machine, it's a simple operation, right? So you can implement it with some electromechanical device as well. The issue is that the keys are long, so they're as long as the plain text, right? When you have to encrypt 1,000 bits, to think of an IP packet 1,500 bits or so, you have to do 1,500 bits of the plain text, of the key, sorry. By the way, do you all hear these calls? So it's unfortunate, but I'm called by someone during the lecture. And do you guys hear it? I don't know how it looks on Zoom. I get like, phone calls.
Yeah, we can hear.
Oh, God. Okay. Sorry about that. I'm not really sure.
Yeah, but it's not too loud.
Okay, great. I'm not sure how to technically stop it because like I have to be online. So therefore they have to call me, I guess, if they insist on doing so. All right. Okay. So that's going to be a significant limitation. But now let's think there's like, what is the security of a one-time pad? Well, what is security at all, right? We kind of have not yet stated this in any form of fashion. Like, what is really a secure? We had some sense of what's insecurity when we went over classic ciphers and we said, like, okay, here is how you can decide what is being said in a message, right? Because you can brute force. The key space is not really large. You can identify if you assume that the message comes from certain distribution, like English text. But obviously, what is security? Let's first look at some straw man examples. For example, can you say that given a ciphertext, given a ciphertext, you can you compute the key? Okay, and so the funny thing about the one-time pad is that you can, because the ciphertext is an XOR between a key and a message. So for any guess of the message, you actually can compute the key. All right. So if I see this one-time pad cipher, and then I say, okay, how about perhaps you said that you encoded, you use it to encrypt a given message. Well, that will be the key that you would use. And I know I can compute it. I do this. I can compute it for any message guess I have. You will see in a second that actually means that exactly implies that it's secure, okay? But like, let's see first how to define this. Yeah, okay. So here is why you can compute it, right? Because you XOR, if this is the equation for the ciphertext, then if I XOR M to both sides, I get C XOR M on this side. And on this side, M is going to drop out. So I'm just going to get a key K, right? So it's just that inverting XOR is XOR again. That's all this says. So security does not exactly mean that the key is secret, or at least that's it's not secret after you use it. Let's consider what are the adversary's capabilities that we want to, let's set them clearly for ourselves. So attacker's abilities is that he gets a ciphertext, only ciphertext for now. Perhaps what we're going to say, that he cannot recover the secret key, but that is not, well, so it wasn't quite true for one-time pad. And also, look, I could instantiate encryption in this obviously wrong way. And encryption of the message is just message. Key is obliterated. If this is a ciphertext, then clearly you cannot recover the secret key. Neither do you have to, because it wasn't even used. But essentially, an attempt at capturing what secrecy, this is a counterexample, shows that it doesn't quite work this way. Even if I say that I cannot recover all plain text, well, that's not going to be good enough. Because like, what if you use this following encryption? I take the key, and my message is really 2 blocks, M0 and M1. I give out M0 in the clear, and I apply the key only to M1. Well, I'm going to argue in a sec that one-time pad is a secure encryption. It protects privacy of M1 well, but M0 was leaked for free. So it is true about this encryption that viewing it does not allow you to learn all plain text because M1 is protected, but it leaks half the plain text. Which my point is, it does not work to say that encryption is secure as long as all plain text cannot be recovered. Recovering some suffices to, it would not be a useful encryption notion. Claude Shannon, around the same time as Vernon, Claude Shannon is basically like the father of information theory about information content. What does it mean that one message has more information than the other? Can we quantify information? Can we reason about it? It is clear, this is like incredibly useful and a sort of groundbreaking theory when it was proposed. In particular, he defined what would it mean for a ciphertext to contain no information about the plain text. And that is the notion we have of perfect secrecy, of so-called information theoretic secrecy, because that whole branch of science invented by Claude Shannon is called information theory. Oh, sorry, I said roughly at the same time. I was wrong. Different war and after it. Cipher ED over this key space is perfectly secret if, okay, so if it is the case for every M0 and M1 in the message space, and we are going to make a limitation that the length of these messages are equal. Recall that if I define a message space as n-bit strings, then their length is equal by definition. The moment they belong to this message space, they are n-bit strings, so their length is n. And every ciphertext in the ciphertext space, I want the following probability to be the same. The left-hand side is the probability. So again, I have 2 messages in the message space, called M0 and M1. And I have a single ciphertext. I measure the probability that a given encryption, and again, there's no security by obscurity, so encryption algorithm is known, and these key spaces are known. The probability of the encryption for a fixed message M0, it maps it to the fixed ciphertext C. And where the probability goes over? Random keys. Once I have randomized encryption, it will also go over randomization of, right, like a second layer of randomness, which is randomness of algorithm E. But think for now, these are deterministic algorithms, so the only the randomization is over keys. What's here on the left side, it's a probability over keys that the fixed message is mapped to fixed ciphertext. On the right-hand side, I have the same ciphertext, but a different message. And I'm looking what's the probability that that different message maps into the same ciphertext. And what Claude Shannon defines an encryption scheme to be perfect is if it is the case that these two probabilities are always the same, no matter what two messages in the message space I'm considering, and no matter what the ciphertext I take, and compare the probability of M0 landing on the ciphertext and M1 landing on the ciphertext. What does this game correspond to? It corresponds to an attacker who knows, you know, the only thing I wonder is if with this n-bit string that you send, is it equal to M0, like I love you very much, or M1, I cannot stand you. I know it's one of the two, and I want to know which one. Now, I observe that you transmitted certain ciphertext. So my question is, does this ciphertext, is it any different? Because you had a random key. I knew you had correct software. So you created this key at random and you ran this correct algorithm on it. So what was the probability that M0 would map to the ciphertext versus what's the probability that M1 did? If these probabilities are the same, then the ciphertext I observe is intuitively does not let me decide, did you encrypt M0 or did you encrypt M1? It gives me no guidance. It doesn't skew. Even if you do it millions of times, you get one ciphertext one day. But the probability that it came from M0 and the probability that it came from M1 is the same. So I cannot use the ciphertext to kind of help me decide which one is the case. I observe you the next day, C prime. Again, probability of C prime, because it goes over all ciphertext, that it resulted from encryption of M0 or it resulted from encryption of M1, they're again the same. It is intuitive, therefore, that this is notion does capture, that the ciphertext is somehow useless. It does not let you decide this game. And that is true for any messages. So, you know, if you had 3 messages, it would be, again, the probabilities would be the same. If the message varied and it came from a distribution, you know, let's say I want to just know, are you talking English or are you talking French in your message? M0 would not be a fixed string. It would came from a distribution of encodings of English sentences. M1 will come from a distribution of encoding of French sentences, right? And yet this notion would generalize to M0 and M1 coming from a distribution. I cannot use the ciphertext to decide which one is the case. So again, this is the notion. Let's look at this some more. So let's think for any message and a ciphertext. Message in a plaintext space, ciphertext in a ciphertext space. Let's call PMC as the probability that M gets encrypted over C. The probability goes over the keys. So for example, let's say that P of MC is 0. That means that there is no key that M gets encrypted as that C. If it's non-zero, that means that the key exists, right? And what Shannon, this notion is equivalent to, it says that these probability functions have the property that for any C and any 2 messages, these 2 probabilities are the same. They basically means, therefore, that I could have a function that is indexed just with C. Because let's enumerate all the messages in the message space. You know, I believe that this extra noise now is probably now really disruptive. Hold on, so I will close the window. Okay, it's a little better. So for just have the okay, so enumerate all messages. This is P of M1C, P of M2C, P of M3C. They're all equal. They don't depend on M. There is a single function that is just a function of C that says, basically, no matter what you encrypted, there is some probability, I call it PC, of the ciphertext being output, right? So that's a consequence that it works for any message. So no matter what message you start with, you have the same probability. So therefore, this probability does not depend on the message. So that is okay. So that means that if you have a game where an encryptor has some message and gets a key and encrypts it, well, if he starts with M, this distribution of ciphertext that you see is a PMC function. If he starts with M prime, it's a PM prime C function, PM2C, PM3C, etc. But they're all the same. So it's as if the ciphertext is chosen every time from this fixed distribution PC. And because this distribution does not depend on the plain text, here you go. Encryption looks independent from the plain text. Therefore, encryption didn't carry any information about the plain text. You can think of these encryptions as a random variable indexed by a message. So for every message M, let ZM be the ciphertext that results from encrypting M under a random key. So this ZM is a random variable, right? Like it hits different ciphertext with some probability. Maybe some ciphertext more, some ciphertext never. Okay, it's a random variable. What Shannon says is that for any message, this random variable is the same. So therefore, the ciphertext is really independent of the message. There is some sort of universal ciphertext variable called Z, such that for every M, ZM is, as a random variable, is equal to this variable Z. It's the same, I'm saying the same thing, just slightly using slightly different squint. And that's why it's called perfect secrecy, perfect security, because it basically, what it implies is that the ciphertext is uncorrelated to the plain text. The distribution of the ciphertext can be just sampled on its own without any information about the plain text. There is some sampler that just takes a random ciphertext in a certain way, and it does not take message into consideration even. And it does hit exact same distribution as encryptions of that message. So therefore, encryption of the message, because they can be sampled independently, are useless, as they don't contain information about the message. Here is why one-time pad is perfectly secret, satisfies this constraint. Okay, so look, one-time pad reminder. An encryption under KNM is just an XOR. So an encryption KM is just K XOR M. Perfect secrecy means that the probability for any M0 and 1C is of the following two things is the same. That C is equal to this encryption, and on the right hand side that C is equal to this encryption, where the probability in both cases goes over random case, right, which will be random n-bit string. And equivalently, I can look at it as if I denote output of encryption on M as a random variable, I call it ZM. It's a random variable imposed by a choice random uniform choice of the key. Okay, I choose sample the key uniformly and I output, right? That's what this random variable is. It just says that these two have to be the same for any M0 and 1. So let's prove this form so that any of these variables are the same. Okay. Actually, I will prove something stronger, that regardless of M, ZM for the case of a one-time pad, so where EKM is implemented as K XOR M, that ZM is a uniform n-bit string. If I prove that, then it is particularly it's going to follow that Z of M0 is the same of ZM1 because this is a uniform n-bit string and this is a uniform n-bit string, right? So it will follow. Okay, but we already have this proof essentially. So recall the two random variables we had on this slide a few slides back. Now, one of them is a message. It's arbitrary, and in fact, in this case, it's fixed. The message is just fixed to be M because my claim is for every M, no matter what it is, ZM is a uniform n-bit string. Okay, so let's fix M. But when I create ZM, how is it? It's a E of KM for K uniformly random. So Z is a encryption of message M under key K. So it's K XOR M. But that was exactly on a few slides back, that no matter what this is, in particular when it's fixed, if the key K is a uniform, fresh, independent n-bit string, then the result of this XOR is distributed as perfectly uniform n-bit string. So we already did that, right? Maybe this is a good place to ask questions. Oh, somebody's asked about the depends on the security definition. Well, yes, because my definition here will be perfect secrecy, which sounds as if it's like the best in the world. It is a one-time secrecy. So it's going to be very, very crucial. This definition talks only about ciphertexts that come out of encryption under a key where the key is fresh, which basically means that if you use the same key twice, there's no guarantees of anything, because in all these expressions, I assumed that the probability goes over a fresh random key. That was essentially equivalent to just assuming that the key is used once. Maybe this encryption will have properties that you can reuse the key, but it's just not guaranteed. And in fact, one-time pad is like clearly you cannot. You can see that, and that will be a homework exercise too. And there is you will see. So basically, as we go, you will see that this one time versus multiple times, that's the first barrier. There will be others. Intuitively, for example, you can say, well, how about you have access to an attack, to a oracle, which encrypts, uses the key to encrypt anything you ask for. That's going to be called chosen plaintext attack. You choose plaintext, and this poor guy just uses the key to encrypt them. Can you learn what? Can you use what you learned from such interactions to break security of some other usage of the same key? Okay, so that chosen plaintext attack, chosen ciphertext attack, we'll see these later. So there will be stronger notions of security than we have right now. Okay, so maybe I'll go on. Okay, so here is an alternative elementary proof. So this was a beautiful proof, right? Like, I mean, kind of like, okay, so maybe somebody got confused, but if you think through it, then you will see, okay, this is a very concise sort of way. So hopefully I did carry it to some of you, and somebody else you might have to review this, but it is a a concise way to say what's going on. But it might not be easy to repeat it. It might not be easy to use it in some other context. So here is a more elementary reason for the same thing in our case, that one-time pad is secured. So let's evaluate this expression. So Shannon says it's okay, it's secure if for every M0, M1C, these two probabilities are equal. Okay, let's try to evaluate these probabilities. So I'm not going to say whether M is M0 and M1 is going to work for both of them. So let's take any M and C and look at this probability. Well, it's if encryption is deterministic, then I can just count keys for which it is true that M on that key is mapped to C. That's in my numerator, and divide by all possible keys, right? So that is the probability that over keys that this is true is simply the probability of hitting a key that makes this true. And if it's deterministic, then it's either true about some key or it's not, right? So you count the keys. And so if it happened that your cipher has this probability E, encryption E, has this property, that for any M and C, for any message in a ciphertext, this count of keys, the count of keys that map this message into the ciphertext. So you fix message and ciphertext pair, and you count how many keys map one to another. Let's say if the encryption has this property that this count always comes out to the same. It does not matter what M and C was. It's always the same constant. Then encryption is perfect secret. Why? Because this means that this top part is always that constant. So let's call that constant C. So this probability is C over the space of keys. Sorry, not C, because C was the ciphertext. Okay, so let's call this constant alpha. So it's alpha over the size of key space. And for any MC, this probability is always alpha over key space. So therefore, the left-hand side here is alpha over key space. The right-hand side is alpha over key space. End of proof. They are the same for any M0, M1C, right? And this counting of keys is very often easy. So let's look at the one-time path. You're fixing message and a cipher. How many keys map a given message to a given cipher? Okay, and so I guess you are not used to writing the stuff on the chat, but the answer is this, right? So it's exactly one key, and it does not matter what a message in a cipher is, because from this equation of encryption, right, for any message and any ciphertext, there exists a key that maps M to C. And this key is deterministically determined by M and C. It's just an XOR of M and C. So that's why it exists, and it is unique. And so that's why, to remember, like at some point we said, oh, okay, is it a bad thing or a good thing that you can compute a key given MC? Well, actually, in this weird way, it's a good thing. It's a proof of security that for any M and any C, there exists a key that explains this correspondence. And it's the very fact that you can compute it, and also that it's unique, right? And so there's only one, that immediately implies a proof of one-time path secrecy, right? Because this basically means if you go back here, right, that all these probabilities are 1 over key space. So for any MC, the probability that they are mapped is 1 over key space, which in the case of one-time path is 1 over 2 to the n, right? Because these are n-bit strings, so there's 2 to the n of them. So it's 1 over 2 to the n for any choice of message. So if I observe a cipher, probability, no matter what message you start, is exactly 1 over 2 to the n and it doesn't matter what message. Okay. So you will see that this funny thing between, is it good that you can compute a key if you have some hypothesis of what the message was? And maybe a natural response would be, that doesn't sound like a good thing. But actually, in this case, not only was it a good thing, it was like a beautiful, like super good thing. This is why it's secure. So this type of thing you will see in cryptography all over the place. Something that perhaps is a problem in a cipher. Perhaps it's like too easy to create something. Perhaps there is too much freedom. But if you turn things around, that freedom was and gave you a security argument. Perhaps constraining things is a good thing. You know, it seems like something is hard, but now it's actually proof and a security argument that became not clear. Perhaps actually it is clearly destroyed. So the complications in the design translated into not only that it's hard to think about security of this, but actually with some more thinking, you decide that it is not secure now. This kind of double-edged nature of security arguments, you will see you know, a constant melody in this stuff. So why is this elementary proof, you know, significant? Because basically, whenever you have a deterministic encryption and a case where the key is chosen uniformly from some space, then you basically can do arguments like this, like determine, take a set for every MC of keys corresponding to this MC pair that map M into the C. Okay, and encryption is perfectly secure if these sets have same number of elements. Okay, so technically for every C, they have to have for any, you know, whenever I succeed, then when I vary M, these sets will have the same. And it's also if and only if. So if you find some M0, M1C, some triple of cipher and two messages, such that there is more keys that can map M0 to the cipher than there were keys that can map M1 to the cipher, then encryption is bunk. Like you shot it, right? That's it. That's a proof that is not perfectly secret. Because you basically immediately get like a contradiction in this equality of the probabilities from that. So all you really have to do when somebody says, okay, I will do on the homework, right? So I will post it after the lecture. Here is some variant of shift cipher. Decide whether it's perfectly secret or not. You will count keys and you will see whether you can argue that for every M and C, the number of keys is the same. If there is some message cipher that there's different number of keys, then that's a counterexample. And most of the time, it will be even simpler. You will not be, the counting will be easy. The key will be only exist, and it will be 1, or it will not exist, so it will be 0. Okay, although that actually, even on the homework, there is an exercise that it's not like that, not exactly that. Like there could be many keys and they're kind of all equivalent, but in a sense, there is different keys. Okay, so that's a user guideline for like how to make these kind of arguments, right? This slide. And here is sort of the limitation that I was saying at the beginning of the class. So one-time pad is great because it's very fast. But the problem is you just XOR, the simplest operation there is. But the problem is that is it coincidental that your keys were as long as your message? So if you wanted to encrypt 100 bits, you had to have 100 bits key. But if you want to encrypt, 1 megabyte, then you have to have 1 megabyte of a key, right? it is called one-time pad, precisely for this reason. The way it was used over larger alphabets, not binary, but let's say letters. And that's basically shift cipher. For every, I had like 100 letters. And so my message was 100 letters. And position by position, I applied not XOR, but addition mod 26 or whatever, 27, right? Number of letters. It is, this addition, modular addition, has the same exact properties. The properties that you need of an XOR, which were, oh God, where is it? This, that you take a message in a larger alphabet, a key in larger alphabet, you do position by position mod, whatever the modulus addition mod done. If then you do another, the decryption is now subtraction. So it's subtraction of the key mod the same modulus. And of course, addition here and subtraction here cancel out. So you get back the same thing, right? So it's as correct, but also this thing works the same way. So in this elementary proof, in the shift position by position, right? You, for any, or actually this one, even easier, right? So you will count the keys that take a certain message to a certain ciphertext. How many keys there are? 1. Right, so for one message and one cipher, so you have a message in the keys in the message space cipher. So these are single letters. There's exactly one shift that maps a message to another, right? So if the shift cipher is position by position, right? So you encrypt 100 characters with a key that is of length 100. It's kind of like Vern, I guess it's the Vignere cipher with 100 shifts. That's where the word one-time pad, okay? Because the spy had 100 of these letters, so it's technically Vignere with 100, and was applying it. And why one time? Because he used it for one, or she, for every letter separately, and then had to just never use it again. If you reuse a one-time pad, security goes down, and that's exercise 3, I think, on the homework. All right. Okay. So where is the, but still, what the poor spy has to do to, if she or he has this 100 character key, cannot do more than a 100 character message, has to get back somehow to the home base or get a new key material somehow. There is no way to hike it up. And in fact, this is a fundamental thing about perfect secrecy. Key space must be longer than a message space. In other words, if you think of these as bits and these as bits, so if these are of length n prime, the keys are n prime bits, and messages are n bits, the only way to satisfy this is that the length of the key must be at least the length of the message, right? So let's see why that is. Let's assume deterministic encryption again. And so let's count the keys, right? Like, so for any M and C, let's this be K of MCB is a set of keys that map M to C. Perfect secrecy says that for any triple of ciphertext and 2 messages, M and N prime, these key sets have equal number of keys in them. Well, in particular, it means that they are non-empty. Because if one was empty, then all the others are empty. But that's nonsense, because that basically means that the cipher is never hit. So you can just as well kick it out from the ciphertext space. So any cipher that can be hit by any message immediately implies that every other has to hit it. So any meaningful ciphertext, attainable ciphertext, it has to be that for every message, the number of keys is at least 1. Now, by decryption correctness, for any C, these sets must be disjoint for different M's. So the keys that map M to C must be different from the keys that map M prime to C. Why is that? Because otherwise decryption would have problem decrypting. If there was a key, let's say that these two intersected, so that means there is a key which is both in this set and in this set. Let's call it a key in the intersection. What does the decryptor do if his key is the key in this intersection and they get ciphertext C? Do they decrypt M or do they decrypt M prime? The decryption is deterministic. Even if it was randomized, it basically would have to guess whether to output M or M prime, and therefore correctness would be violated. All right. So these for correctness, these spaces of keys have to be distinct. So therefore, these key sets, they partition the space of keys. And because they are non-intersecting, if I take their union over all M's in the message space, so I fix C, and then I vary over messages in the message space, and each message gives me a set of keys, and the set is non-empty, and for each message, the set must be different because they cannot intersect. So how big is this space of when I take a union of all these? It must have as many elements as M, right? Because for every message, I had a set, and these sets were different. For every message, there was a different set. They were all non-empty. So they must be all of them must be at least as large as the number of messages. So I conclude this. You know, the key moments in this proof was perfect secrecy, so that these key sizes are the same. So therefore, this strict requirement, so none of them is empty. And decryption correctness, which means that they are non-intersecting. On a kind of like a bonus, I mean, like a more advanced homework problem, you will see that if you relax either secrecy in some way or correctness in some way, then you can beat this bound. But it will be either at the price of correctness, which nobody wants to pay. You know, what's good is the encryption, which like with 1/2 probability decrypts the correct message, or at the price of secrecy. It has to, but in a quantifiable way, you can sort of look at the some variants of this. Other than that, we are stuck with this, and this is a fundamental bound. So here is what it also shows is that, hey, if somebody gives you an encryption scheme, and this is not the case, so somehow the number of keys is less than the number of messages, then you can immediately say, this is not a perfectly secure encryption. It cannot be because of this implication. If I ask you to give an explicit counterexample, like where does this notion fail? Like show me 2 messages that encrypt into some ciphertext with the different probabilities, then you have to find them. But if you just have to say whether it's perfectly secure, you can say, no, it's not, for sure, it's not, because this bound is violated. And then you can see that for these classic ciphers, you know, if I have a shift cipher, so there's only 26 keys, but I try to use it, not like in this one-time way that I was saying, but for a single shift for more than 1 character, well, then it immediately violates this, right? Because there is space of keys is 26, but space of messages is 26 to the power of n, where n is the number of characters. So it could only be secure for n equal 1, right? The same for a two-time pad. If you try to reuse the pad, well, like think of messages as 2 n bits and a key n bits, and you use the n bits first on the first n bits here of the message, and then the same key on the next n bit chunk, right? This has 2 to the n, and this has 2 to the 2n. So no way this bound is satisfied. But if I ask you like, okay, but explicitly show me, you know, okay, so it's not perfectly secret, but like give me some explicit attack and I specify what I mean by that. Then okay, maybe you have to think a little bit. Okay, so I think